Hello mathematicians, welcome back to another video, linear functions yet again, and if you want to learn more about linear functions, make sure to check out the link at the top of the description as well as the info box. You can find the complete playlist up, down and up there, basically with everything that's going to be ever covered during your school life regarding linear functions. And today we would like to talk about the first geometric aspect that you are probably ever going to encounter during your school analysis calculus, namely, what is the area under the graph of a linear function? And we are going to motivate the idea today. What area is it exactly? And after that we are going to calculate through a standard example that you can probably find in some textbook somewhere. I'm going to come up with a function, but yeah, basically the idea behind it is well known. So now we are going to dive right in. So at first we are going to imagine how a linear function could probably look. So a linear function can be in a coordinate system in some way, and it can look like this. And now someone could ask the question, what is the area which is bounded between the zero of the function, so for example the root, where we pass through the x-axis, and let's say x being equal to 4. Okay, this right here is x being equal to 4. And now we are going to ask ourselves the question, what is the area under this curve? Now there's a geometric figure hidden in this graph, which is kind of obvious if you ask me. What about extending this line here, like a vertical line starting in 4. And now it might be clear to you that the area under this graph is nothing but a right triangle. If we were to find out the area of this right triangle, we are done with the job. It's not going to get any harder than this, honestly. Later, when we are going to talk about integrals, we are going to get a very nice generalized formula for the area under this curve, anywhere in the coordinate system, but then there's going to come out a part 2 of this video, alright? This right here is part 1, basically. So now, we are going to motivate the idea behind the area under this curve. And it's really easy because if we were to duplicate this triangle right here, we are going to act like we can duplicate this triangle. We are going to turn it around a tiny little bit and just put it here. Okay, I hope you can follow my idea. We are going to take this triangle, we are going to take it times 2 and just put it here. And now it's a bit cooler because this right here is nothing but a rectangle, and the area of a rectangle is really easy to calculate because the area of a rectangle is just the base, A, times the height, B, that we are going to have. Okay, if we were to get the area or calculate the area of this whole rectangle, we are going to get that the area is hence nothing but A times B. But do not forget, this right here is twice the area of our right triangle. So what are we going to do to get only the area of one right triangle? Well, we are going to divide this area by 2, and hence we are done. This is the area under this curve. Really easy to motivate. Instead of A and B, when talking about slope triangles, this idea is going to become more important when talking about derivatives and integrals. This A and B can also be interpreted as some delta x and some delta y, so difference in x values and a difference in y values. So do not forget that, but we are going to call it A and B for now. Yeah, and that's basically it. There's nothing more you need to know about this. And now we can start calculating through a nice example. Let's say textbook wants from you that you have to calculate the area under the curve of the function f of x being equal to 3x plus 3, which is bounded between the x and the y-axis. This might seem abstract at first, but it's really easy to see what this area is going to be once we draw a graph of this function. So at first let us get a little coordinate system, and now we are going to take a look. So our y-intercept is 3, meaning it's going to pass through the y-axis, our graph, at y being equal to 3. Okay, this is up here. So right here we have a certain point. Now where's another characteristic point that we can place in the coordinate system such that we can draw the graph by connecting points? Well, for example, if we do it like up here and get ourselves the zero of this function, the root. So what did we have to do to get ourselves the root of this function? Well, what we had to do is we said y being equal to 0, just because our root is the spot where our graph passes through the x-axis, and this happens exactly at y being equal to 0. Meaning, if we were to say 3x plus 3 is nothing but 0, we can solve for x and find out where exactly our x value is right here on the graph where our function passes through. So how can we solve this equation? Well, at first we are going to subtract 3 on both sides. Thus we have 3x being equal to -3. Now all we have to do to isolate x is to divide by 3 on both sides because it's not equal to 0, leaving us overall with x being equal to -3/3, but 3/3 is nothing but -1. This right here is the zero of our function, -1, meaning our graph passes through the x-axis at -1, meaning our graph looks something like this. Hey, and now this abstract formulation of the exercise becomes a bit more clear because the area under the graph, which is bounded between the x and the y-axis, is nothing but exactly this area that we're having here. And now it's really easy to calculate because all we really need to find out is a and b, so the base and the height of our triangle, like the opposite and the adjacent of the hypotenuse. It's basically what it is. So what exactly is our base? Our base in our case, is the distance between 0 and -1. This is just 1. Okay, so our a is equal to 1 because this distance right here is just 1. What is the distance between 0 and the y-intercept? I mean, the y-intercept is exactly at 3, meaning we are going to have 3 units as being our b. And now the area is really easy to calculate because our area is nothing but 1 times 3 over 2 by this formula that we are having here. And 1 times 3 is nothing but 3, so this is 3 over 2, which is 1.5. And now you can say those are area units in some way, AU, okay? So area units in some way, like square centimeters or whatsoever. And this basically concludes the video. This is just a little complimentary video I wanted to produce because it's kind of important to get to know the idea behind areas under curves a bit better. And with linear functions, it's a very nice and easy introduction to the topic. If you enjoyed this video, please like, subscribe, make a comment, channel, like. Don't forget to check out Flammable Maths 1 and also STEM merch. We got some very nice merch going on over there. And other than that, thank you guys for watching. Don't forget to subscribe to this channel, and up until the next video, I wish you guys a flammable day. Ciao!